Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about literal equations. First, let's define a literal equation. Literal, the word actually means expressed with letters, from which we get literature, literary, all that stuff, okay? We're talking about equations. Oh, that's the other part of it, isn't it? An equation is a statement that two expressions are equivalent. In other words, you need to have an equal sign, and you need to have at least two letters in your equation for it to be a literal equation. And usually it's more interesting than that, and you can have a lot of other letters involved also. Okay, but a literal equation is an equation that has more than two variables. So yes, even this very familiar equation could be considered a literal equation. Now, each one of those letters within a given situation has a definition. Let me show you. You have probably seen this equation before. It's part of Einstein's theory of special relativity. And of course, we know that E equals energy, or means energy. M refers to the mass of an object, and C refers to the speed of light. So if you take an object's mass, multiply it by the speed of light squared, you can calculate its equivalence in energy. Let's talk about a more common equation. In New York State, the maximum speed limit, if there is no limit posted, is 55 miles per hour. That's miles per hour. That's a distance divided by a time to give you a speed. We'll talk about velocity later in the course. Okay? That's a literal equation, or could be, if instead of writing out those words, I used one letter for each of them. And I'm going to go ahead and put my speed on the other side. And often in this course, I will write a cursive S so my S doesn't start looking like a 5. But anyways, it's that literal equation in which I am interested. So let's move that up here. All right, we can identify each component of this, the speed, the distance, and the time. This formula holds true whether we're talking about miles per hour, meters per second, feet per minute, or even light years, which is the distance light can travel in 1 year. Let's take a closer look at the literal equation or formula for speed. However, this isn't just the formula for speed, it's also the formula for distance and the formula or literal equation for time. First, let's figure out how we would rewrite this to indicate that it is a formula for distance. If we perform a little bit of algebra here, multiplying both sides by t, I'll put t over 1 here since I'm multiplying by a fraction, I now have distance equals time times the speed. Or, as we would usually write that, distance equals speed times time. So we started with this. Speed equals distance divided by time. We derived the formula distance equals speed times time. If we apply just a little more algebra, dividing both sides by the speed, we will get the formula for time. So time equals distance divided by the speed. So let's look at another equation. Do you recognize this literal equation? Yes, that is the formula for converting between Fahrenheit and Celsius. It's a literal formula. You can use it to convert either way. And now it's time for a story. A few years ago, my husband and I were up in Digby, Nova Scotia in the summer for a vacation. And we were staying at a bed and breakfast. We went out to the ocean during the day. We got back, and our host said, Wow, it was amazing here. It got up to 34 degrees Celsius. She was expecting us to say, "Wow, that was awful. How did you stand it?" And all she got were blank looks because being Americans, in our mind, we were trying to do this conversion from Celsius to Fahrenheit. This is the equation that I remember easiest because I can remember that here is freezing, and that's at 32 degrees Fahrenheit. So if I subtract the 32 from a Fahrenheit temperature, I know that the Fahrenheit degrees are also smaller than the Celsius, so I'll have to do multiplication by 5/9 rather than by 9/5. So, it's kind of complicated. That's just the way my mind works. Okay. But she wasn't giving us Fahrenheit, she was giving us Celsius. So we had to do some mental gymnastics with this in order to figure out what is that in Fahrenheit and is that really hot? It would have been easier had I memorized the formula for converting Celsius to Fahrenheit. Well, let's see what that formula would be because we can get there by algebra, right? So I need to manipulate this. I have 5/9 times this stuff in parentheses. I want to solve for Fahrenheit. I want to figure out how hot 34 degrees Celsius is. So if I multiply both sides by 9/5, that gets me closer. So 9/5 Celsius equals Fahrenheit minus 32. And then if I add 32 to both sides, there I have it. I need to take the Celsius temperature, multiply it by 9/5, and add 32. Still not the easiest thing to do in your head, but more doable. So it was 9/5 times 34 over 1 plus 32 equals F. And this works out to be 93.2 degrees Fahrenheit, which is pretty hot, but hey, this was late July. However, you have to realize Digby, Nova Scotia is pretty far north of here, and their average high temperature in that time in July is 73 degrees. So, yes, she was right. It was miserable compared to the 23 degrees Celsius they were used to in the summer. Now, if I had to convert between Fahrenheit and Celsius often, even though this equation is easier for me to remember, I wouldn't want to use it. I would want to manipulate it, as I just showed you, and work with this equation, just plugging in the Celsius degrees right there. That's the power of literal equations. You can solve them first for whatever you're going to be looking for, and then use this new formula to do your calculations instead of having to do algebraic manipulation every time with every new number. All right, quick quiz. What is this? What do you call that? And what is this? Next question. Is that a true statement? Well, it depends on how picky your search engine is. But mathematically, the answer is, if it's in the same literal equation, no, they are not equal. We use capital letters and small letters to differentiate between variables in literal equations. So Newton's law of gravitational attraction or gravitational force between any two bodies in the universe is F equals G times capital M times small m divided by r squared. Right? The F here does not mean Fahrenheit as it did in the previous literal equation. Here it stands for the gravitational force between the bodies. The capital M is the larger body, say the sun. The small m is the smaller body, say the earth. And r is actually the distance between the centers of the two bodies. G, interestingly enough, or maybe not, maybe you're not as much of an astronomy geek as I am, G is a constant. It is the universal gravitational constant. When comparing the Earth and the Sun, it is pretty obvious that their masses are different because the sun is massive. So let me ask you this. Is y sub 2 equal to y sub 1? They're both y's. However, they have different subscripts, so they are not equal. You should be familiar with this use of subscripts from this formula. Okay, the formula for slope, of course, where x1 and y1 refer to the coordinates of a point on a Cartesian plane, and x2, y2 refer to another point on the Cartesian plane. And also a variable without a subscript does not equal a variable with a subscript. In this case, t often stands for time. This would be the initial time, and the t would be some other time that's not your starting time. Here is another literal equation with which you should be familiar. This is the formula for the circumference of a circle. C equals 2 pi r. How many variables are there in this equation? This literal equation actually only has 2 variables. 2 is, of course, a constant. And remember, pi is also a constant. Sometimes we will use Greek letters for variables, but in this case, pi is a definite number. And pi, by the way, is the exact value. It's an irrational number. It is approximately 3.1415, or approximately 22 sevenths, but neither of those is the exact answer. Many times in this course, I will ask you for exact answers. And if that exact answer involves pi, do not substitute 3.14 whatever or 22 sevenths. Give me your answer with the pi in place. All right, but instead of having the formula for circumference, let's figure out from this literal equation what the literal equation for radius, or the formula for radius, would be. So in other words, we're going to solve this for r. We're going to solve a literal equation for the variable r. I need to isolate r in order to do that. So I'm going to divide both sides by 2 pi. Because after I have done that, yes, that r is isolated. If it makes you feel better, you can switch both sides, rewrite it this way. That's fine. But that is the literal equation for r, given the circumference. So let's move our new literal equation up here, and let's see what we could do if someone told us that the circumference of the circle in question is 22.00 centimeters. Okay, we have r equals 22.00 divided by 2 pi, remembering that at the end I'm going to have to use my units of centimeters. Now at this point, if I want an exact answer, the most I can do is cancel here. 2 goes into 2 once, 2 goes into 22.00, 11.00 times. So my exact answer for this would be r equals 11.00 divided by pi centimeters. That is an exact answer. All right? But in the real world, you usually have to go and measure something. So you're going to have to approximate the answer based upon the precision of your measuring instrument. And in this case, if you punch into your calculator 11.00, or just 11, because it's your calculator, you can get away with that, and divide it by the pi button on your calculator, you're going to get 3.501 centimeters. And that is an approximate answer. Approximate answer. Let's look at one more complicated example of a literal equation. Forgot my sound effect. All right, here is a literal equation, and I'm going to solve this literal equation for capital M. Now, this happens to be an equation that deals with pulleys and masses and gravity and all that, but what you need to have is the literal equation and the variable for which you are solving. So let's do this. Moving that over a little bit so I have a little bit more room. I need to solve for this capital M. It is in the denominator right now. Not good. I want it in the numerator. I want it isolated by itself. So first thing I'm going to do is to multiply both sides by capital M plus 2 times small m. And when I do that, this will cancel. That will leave me 2mg on this side and m plus 2m. I'm going to leave it in the parentheses because that is all multiplied by a still. Now I want to isolate, still trying to isolate that capital M. So what can I do now? That capital M is still trapped inside those parentheses, but that whole thing is multiplied by a. So I am going to divide both sides by a, leaving me capital M plus 2 times small m. There's nothing to multiply it by, so at this point I can drop those parentheses. And on the other side I have 2mg over a. There's no canceling to be done. There's no division I can do. I have to leave it there. Now I still want to isolate capital M. I'm going to subtract 2m from both sides. Now I have capital M equals 2mg over a minus 2m. Have I completely isolated it? Yes, I have. That may not be the most useful form of this, though, depending on how easy it is to punch things into a calculator, or depending upon whether you are calculating this all by hand. Another form may be more useful. So here are some other forms you can have of this literal equation. I could go ahead and do the subtraction that is indicated there. However, I would have to first get 2m over 1 equal to something over a, so 2ma. Another form of this literal equation would be 2mg minus 2ma over a, which is looking good, but maybe it would be easier to use it in the form 2m times g minus a. I have taken out the greatest common factor there, and that's all over a. Have I isolated m there? Yes. Have I isolated m in this equation? Yes. Have I isolated in this one? Yes. This is an applied course. Decide which one is most useful for you in the situation you find yourself. Literal equations. They are literally very powerful and very familiar to you as formulas. I'll see you in class.